Hello! In this trigonometry lesson, we're going to take your definitions for the trigonometric ratios and push them a little bit further, defining those ratios for all angles by using the coordinate plane. Now, you may not realize it, but as of right now, your definitions of trigonometric ratios are fairly limited. And by that I mean they are limited to angles that are acute. We have found the sine, the cosine, the tangent, and even those reciprocal cosecant, secant, and cotangents for all sorts of acute angles. And we did that by defining those ratios on a right triangle. The sides of that triangle helped us determine the sine, cosine, or tangent of that angle. So here we've got a nice acute angle sitting in this right triangle. The sine is defined as the length of the opposite side over the hypotenuse. But that's a fairly limited definition because we've seen that angles aren't always acute. You knew back in geometry that angles were obtuse, and you learned now in trigonometry that angles can have measures that are negative or measures that go way beyond anything that could fit inside of a right triangle. However, angles larger than 90 degrees do have trigonometric ratios associated with them. The trouble is, triangles cannot help you to find the sine, cosine, or tangent of that angle. There we go. Here's a triangle with an angle bigger than 90. I could not use SOHCAHTOA to find the sine of this angle because there is no hypotenuse and it's hard to know which leg is the opposite leg when there is no hypotenuse. So what we have to do is take your definition for sine, cosine, and tangent and expand it. Push it into another realm, if you will, so that we can find sine, cosine, tangent, or reciprocal ratios for any angle. Doing so requires us to use the coordinate plane. To define trigonometric ratios for all angles, we place our angles in the coordinate plane and relate the sides of the triangle to the coordinates of a point that the terminal side of your angle passes through. If you need a visual, well, here's a visual right here. I have placed my angle in the coordinate plane along the XY axis. Here is my angle. I can now relate the sides of this triangle to the coordinates of a point that the terminal side of my angle passes through. And let's draw that terminal side. This would be the initial side, and this would be the terminal side of our angle. And let's just say, for the sake of argument, even though it doesn't really show what direction this angle rotates, we'll rotate it simply in the counterclockwise direction. The sides of this triangle can now be related to a point, a coordinate that the terminal side of my angle passes through. And I could tell you the coordinates of that point by using the sides of this triangle. The sides that are adjacent and opposite the angle can now be described in terms of a point on the terminal side of this angle. The adjacent side matches up perfectly with the x-coordinate of this point. The x-coordinate of that point is 3 because this point travels 3 units to the right. The opposite side is the y-coordinate. The y-coordinate of this point would be 4 because vertically we move up 4 units. And the hypotenuse of our triangle is represented by the distance between this point and the origin. How far is it to the point 3, 4 to the origin? Why, it's 5 units. And the Pythagorean theorem would confirm that. I can now think of sine, cosine, and tangent in 2 ways. One way you already know, by thinking of those ratios as ratios of sides in your triangle. And the second way we will learn right now by thinking of those ratios as relating to the coordinates of a point that our angle passes through. So here is a definition of trigonometric ratios by using the coordinate plane. And this information can be found in your book on page 444. So suppose I have an angle theta in standard position, and P is some point on the terminal side of our angle, whether it has coordinates 3, 4, or just generic x, y in this case. We're going to define the variable r as being the distance between this point and the origin. How far is it from this point to the origin? Well, when I had numbers, I could use the Pythagorean theorem to find this distance. And when I have variables, I can still use the Pythagorean theorem. The distance from this point to the origin can be thought of as x squared plus y squared. That would be equal to this distance r squared. It's the Pythagorean theorem with these variables in place. So if I want to know the distance from x, y to the origin, I can take the square root of both sides and find that that distance, which we're calling r, can be calculated as x squared plus y squared, all rooted. Now I can take the ratios for sine, cosine, and tangent and rewrite them in terms of x, y, and r. And I'll say that one more time. I can take the ratios for sine, cosine, and tangent and rewrite them not in terms of legs, but in terms of x, y, and r. And I'll do that in a little progression. The sine of theta, if I'm thinking of right triangles, is expressed as the length of the opposite side divided by the length of the hypotenuse. But if I take that same ratio and relate it to a coordinate that the angle passes through and the distance from that coordinate to the origin, the sine of theta is expressed as y over r. Y stands in as the opposite leg, and r stands in as the hypotenuse. The y coordinate that this angle passes through and the distance from that coordinate to the origin, a ratio of those two things, is another way to calculate the sine of an angle. The sine is still opposite over hypotenuse when you're working on right triangles, but this gives you a second way to calculate or think about that ratio. The same is also true for the cosine of theta. Right triangle trigonometry taught us that the cosine of an angle places the length of the adjacent leg over the length of the hypotenuse. But if I've got an angle that's larger than 90, well, then the right triangle doesn't help me anymore. Maybe I can use a coordinate that the angle passes through instead. The x coordinate stands in for the adjacent leg because they would be equivalent to each other. And that distance r stands in for the hypotenuse because it's truly the distance from that point to the origin, the length of this piece right here. So the cosine of theta can now be thought of in two ways: adjacent over hypotenuse, good old SOHCAHTOA, or the x coordinate that the angle passes through, divided by that distance r. And then lastly, our friend the tangent of theta. When we're working with right triangles, SOHCAHTOA tells us to place the opposite leg and divide it by the adjacent leg. That's our ratio for sides in a triangle. But when I relate it to the coordinates that the angle passes through, I would take the y coordinate and divide it by the x coordinate. Now, these ratios do not erase what we already know is true about sine, cosine, and tangent. They just provide us with an additional way to calculate them. The sine can be calculated by taking the y coordinate your angle passes through and dividing it by that distance r, calculated here. Put a nice little box around it. Okay? Same with cosine. Cosine is still adjacent over hypotenuse when you're working with right triangle trigonometry. But when your angles can't conform to a right triangle, you need another way to deal with that ratio. X over r is another way to calculate the cosine of an angle. Now, let's practice that. Find the sine, cosine, and tangent of an angle whose terminal side passes through this point. And I've gone ahead and drawn us a nice little picture here. Notice they don't give us the measure of the angle. I don't know which direction that angle even rotates. It might rotate in the clockwise or counterclockwise direction. But for the sake of argument, let's go ahead and just say that it rotates in the counterclockwise direction and looks like that. That angle is way too big to fit inside of a right triangle. So there is no way that I could use SOHCAHTOA to find the sine of this angle. If you even tried to rotate it in this direction, whatever angle measurement that is negative. And drawing a right triangle with a negative angle is not something I learned how to do in geometry. So that means SOHCAHTOA is not sufficient to find the sine, cosine, or tangent of this angle. Thankfully, we have some additional ways to do that. The sine of theta is equal to the y coordinate that this angle passes through in the coordinate plane divided by the distance from that point to the origin. The y coordinate I already know is -2. What I need to calculate is what is this distance r from the point to the origin. That's what that is right there. Calculating that is fairly straightforward. R is a distance calculated using this statement right here. It's the Pythagorean theorem with these coordinates. So I would have 3 squared plus -2 squared. That would take me to 9 plus 4. Let's actually write down a 9 plus 4. Remember, when you square a negative, it becomes positive because you're taking a negative number and multiplying it by itself. That means the distance from this coordinate to the origin is the square root of 13, which we will leave in its radical form. Otherwise, I'd have to have a decimal approximation, and I'd rather have an exact value. So the distance from the point here to the origin is the square root of 13. That means the sine of theta is -2 over the square root of 13. I would then ask that you rationalize by multiplying the top and bottom by the square root of 13, giving us a ratio for the sine of this angle that is equal to -2 root 13 over 13. A couple of things to marvel at with this answer. Number one, you just found the sine of an angle that's bigger than 90 degrees, or maybe even less than 0 degrees, because the sine of that angle cannot be calculated using triangles. We had to use a different method. The other thing to notice here is that the sine of this angle turned out to be a negative value. That's right, trigonometric ratios can be negative. And this trigonometric ratio has to be negative because this angle passes through a y coordinate that is negative. Let's find the cosine of theta. We've already done a lot of the hard work. The cosine of theta, when we are using a point on the coordinate plane that your angle passes through, is x over r. So I take the x coordinate our angle passes through, which is 3, and divide it by the distance from that coordinate to the origin, already calculated at the root 13, and I rationalize accordingly. Always make sure that you rationalize, meaning the denominator does not contain a radical. That is something that you learned about in a previous math experience. The cosine of this angle is 3 root 13 over 13, x over r, the x coordinate divided by this distance. And then lastly, the tangent of theta, which we could have calculated right off the bat, because when we are using the coordinates of a point that your angle passes through, the tangent of the angle is the y coordinate divided by the x coordinate. SOHCAHTOA still works, but not when your angle is beyond right triangle trigonometry. Therefore, the tangent of this angle theta is -2 over 3. Lovely. All right, what's on the next page? Well, the next page is an example for you to try on your own. So kindly pause this video, and then when you unpause it, I will work through this, and we'll see if our solutions match up. So find the sine, cosine, or tangent of an angle whose terminal side passes through -3, 3. I've gone ahead and drawn you a little picture there. All right, off you go. Pause it now. And you unpaused it. Good job. Welcome back. The sine of theta is equal to y over r. The y coordinate is 3, and the distance r is -3 squared plus 3 squared. That is 9 plus 9. That is 18 rooted, which gives us a great opportunity to simplify this radical. The square root of 18 can be simplified because it has a perfect square factor of 9. The square root of 18 simplifies to 3 root 2. You should be simplifying your radicals. Just like I'm asking that you rationalize your denominators, you should also be simplifying your radicals. This one simplifies to 3 root 2. So I've got 3 over 3 root 2. That is my sine. Even before I rationalize, the 3's would reduce down. Let's call this 1 over root 2. And then now I will rationalize. It just saves you a little bit of work there. So we'll multiply top and bottom by the square root of 2. And I end up with a sine of theta. That's equal to root 2 over 2. Side note, that number should sound a little familiar because we've run into it a couple of times in this class. Let's talk about the cosine of theta. The cosine of this angle can be calculated by taking the x-coordinate the angle passes through and dividing it by this distance r. That would be negative 3 divided by 3 root 2. Let's reduce and rationalize. That's negative 1 over root 2. Don't lose the negative value there. This angle passes through an x-coordinate that is negative. So it's going to have a cosine that is negative. In fact, it has a cosine that shakes out to be equal to negative root 2 over 2. The angle passes through an x-coordinate that is negative, so it has to have a cosine that is negative. And then lastly, the tangent, which we could have calculated right off the bat, is the y-coordinate divided by the x-coordinate. That is 3 over negative 3. Therefore, the tangent of this angle theta is equal to negative 1. Now, notice that in this picture, I didn't bother drawing what direction the angle rotates because it doesn't really matter. The measure of the angle is only as important as figuring out where the terminal side is located. So whether this angle rotates in the counterclockwise, positive direction, or whether it rotates in the clockwise, negative direction, or maybe it rotates in the positive clockwise direction multiple times before finally terminating here, isn't as important as where is the angle located. Does it pass through this point or that point? It's the coordinates of that point, it's the location of this terminal side that really gets you the ratio rather than how big the angle is. I mean, the size of the angle still matters, but it's not as important. Okay, we're going to do one final example here, and it's this one right here. This one can be a little tricky sometimes, so I like to make sure we go through this one together. They say here that the terminal side of an angle of theta radians lies in quadrant 3. Quadrant 3 would be this quadrant right here, because that's 1, and that's 2. And that's 3, and this is 4. All right, and it lies along this line, y equals 2x. Find the sine, cosine, and tangent of theta. Ugh. Well, let's try to draw a picture of this. Initial side, boom shakalaka. Terminal side lies along this line in the third quadrant. Well, y equals 2x is a line whose slope is equal to 2 and whose y-intercept is equal to 0. Because it's y equals 2x plus 0. You've all taken basic algebra. This is something that is an expectation that you know. So let's sketch a picture of this line in the third quadrant, because here's what I really need to know. In order to find the sine, cosine, and tangent of this angle, I need to know the coordinates of a point that the terminal side passes through. If I can find the coordinates of a point that the terminal side passes through, everything else is easy. As long as I know where the angle passes, what point it passes through, I could find the sine, cosine, or tangent. So let's think about y equals 2x. So the y-intercept is 0 here. And up to over 1 is the slope, but that puts me into the first quadrant. This terminal side is in the third quadrant. So let's go down 2 and over 1. And heck, I could even go down another 2 and over another 1. And I've plotted myself some points that the terminal side passes through. And I'll use the nice straight line maker so it looks a little better. Passes through that coordinate, and it passes through that coordinate. So by using my algebra skills, I have determined 2 points that this angle passes through. It passes through the coordinate negative 1, negative 2. And it passes through the coordinate negative 2, negative 4. By knowing the coordinates that the angle passes through, I could find the sine, cosine, or tangent. And it doesn't matter which of these 2 points you use. I would encourage you to use the simpler of the two, That would be -1, -2. So the x-coordinate is -1, the y-coordinate is -2. They didn't give me the coordinates like they did on this previous example. Like, hey, here's the point. Go find sine, cosine, tangent. Instead, they gave me some information that I could then utilize to locate that coordinate. And this is all basic algebra that you've all done before. So it is the expectation that this is something that you can just do. All right. Sine of theta is y over r, which is -2 over -1 squared plus -2 squared. That's 1 plus 4. Remember, squaring a negative is a positive. So r is the square root of 5. When we rationalize that, this is a process that you've done hopefully enough times. I end up with -2 root 5 over 5 for the sine of theta. Sorry, the equal sign's a little sloppy there. It's worse, but let's just call it somewhat better. Here the sign is negative, and I'm not surprised to find a sign that is negative because my angle passed through a y coordinate that was negative. Let's go ahead and find the cosine of theta. That would be x over r, -1 over root 5, rationalizes my cosine ratio to -√5 over 5. My cosine is a negative, and I'm not surprised because this angle, regardless of what direction it rotates or how big it might be, passes through a point whose x-coordinate is negative. And lastly, when we calculate the tangent, will the value of this angle's tangent be positive or negative? Well, I have to take the y-coordinate divided by the x-coordinate, which is a -2 divided by a -1. So I do end up with a tangent of theta that's positive, whereas all the other ratios ended up being negative. Now, none of these examples talked about the reciprocal ratios of cosecant, secant, and cotangent, but it is truly just as simple as taking what we know about sine, cosine, and tangent and reciprocating those ratios. Since sine is y over r, cosecant is r over y, and the other reciprocal ratios follow suit. So if you're asked to calculate those ratios based on a point that your angle passes through, knowing the sine ratio can then lead you to the cosecant. These are facts of trigonometry that you need to know. You will have to know how to find the sine of an angle when you know the coordinate that it passes through. So this is something that should take a very prominent place in your notes, and you should be able to calculate these things by knowing, okay, the cosine is x over r. The tangent is y over r. Reach out to me if you have any questions. Send me an email, message me on Schoology, and have fun doing some trigonometry. Bye.